We're back with Chapter 10, Flow and Conduits, and this is going to be section 10.5. And we're merely going to derive the head loss and friction factor for laminar flow. And we will find out, I'm going to do the full derivation because there are quite a few differences in my derivation and the book's derivation. And I think my derivation gives some more reasonable results. But what we're going to find out, the bottom line, is that the friction factor for laminar flow in a pipe or a conduit is just simply 64 over the Reynolds number when applied to the diameter of the pipe here. Okay, so let's skip ahead to 10.5 and take a look at the derivation. So here we are. We're going to remember from before in this chapter that for conduits, we have laminar flow when the Reynolds number applied to the diameter of the pipe is less than 2,000. And we're going to have smooth velocity through here. We're going to have the flow being in layers or laminae. That's why it's called laminar flow. And mixing is going to be due primarily to molecular diffusion, which is quite slow. And we're going to find out, basically through this derivation, that laminar flow in a pipe is what we saw before, way early in the semester. It's a Poisson flow. So, so we're going to basically derive this equation right here initially. And I want to note that my derivation is going to have quite a few differences in terms of signs. In other words, my derivation is actually going to have a plus sign here instead, because I think there's some differences with the book in how they approach this, and their velocities all come out to be negative, and I believe that it's because they have switched their definition of the what's positive and negative piezometric pressure. So I'll kind of show you that, and you can compare my derivation to that in the book if you'd like. Let me see. Yeah, and you'll see in my derivation, these will also be plus signs, which I think they need to be. A positive mass flow rate and a positive average velocity makes a lot more sense to me. So let's go back, and this is going to be a bit of a lengthy derivation, but let's get going. So laminar flow in a round pipe. We know that this is going to hold true, that the shear stress is going to be equal to the viscosity over the rate of shear strain. We've seen this equation before. And since we're dealing with a pipe, we're going to do a transformation of variables. And this is where I first differ from the book. They used a different transformation of variables, and I'm just going to transform y into r so that dr equals dr dy equals 1. And so this gives us tau of mu d dr, dv dr, okay, with a positive sign. But we also saw from before that from before that tau is also equal to minus r over 2 dds of the piezometric pressure. And I believe that what's going on here is that the book is defining this to be from 2 to 1, 0.2 to from 0.2 to 0.1 in the flow, and I'm actually defining it from 1 to 2. And so there's a minus sign in the piezometric pressure that I'm not going to carry through because that's why their velocities, and let me just skip ahead here for a second. That's why, that's why their discharges and their velocities are all coming out negative and mine are coming out positive. It's because they're defining basically this different, and they're coming up with a negative sign all the way through their flow, their equations. So let's just bring up um, a new form. What we're going to do first is we're going to combine these two equations. Since they both equal tau, we can combine them. So let's go ahead and do that. And what we have is, if we rearrange slightly, we've got minus 2 mu over r dv dr. And that's going to equal the change in the piezometric pressure. All right, and we note that over here, these are just a function of r. These are all functions of r, and these are all functions of s. And I agree with the book that because of this, we can set DDS, or both of these equals a constant here. We'll just call it constant, and therefore we can rewrite this as a constant. And in fact, we can manipulate it as the book does to just rewrite it like this. Since the piezometric pressure is constant along the pipe, we can just rewrite it like this, where this is now the piezometric head. And we'll see in a minute as we go through this derivation, we'll write this and it will be 1 minus 2 instead of 2 minus 1, because we're not going to carry this minus sign through. So now that we have this nugget here, we can plug back into the equation that we had on the previous page, and dv dr now becomes minus r over 2 mu times gamma delta h, the change in piezometric head over the length of that we're interested in. Okay, so there's our equation, and we need to integrate this. So we move the dr to the other side, and we're going to do an integral from 0 to v dv, and we're going to pull out the constant in front here, minus 1 over 2 mu, and then we have the piezometric head constant that we had before. That's a delta there. And our integral with respect to r now is different than the books. This is just from 0 to r of r dr, and that's an r there. And so when we do this integration, we're going to get v on this side. It's just going to be v minus 0. And we're going to have minus 1 over 2 mu gamma delta h delta L, and we're going to have basically r squared over 2. We're going to apply that from 0 to r, which just gives us r squared over 2 back, and we also have a constant of integration out here. And now we can apply the boundary condition. The boundary condition, and the easiest boundary condition to apply is the one at the wall here. Anywhere along the wall of the pipe here, we're going to have that the velocity has to be equal to 0 because the pipe's at rest. So writing that out formally, we have v of r equals r0 at the wall is going to equal 0. And plugging that in to this equation here, we have 0 equals minus 1 over 2 mu gamma delta h over delta L, and this is r, let me make sure this is correct, r0 squared over 2, and then we still have this constant of integration. So we can see that c is going to basically equal this positive thing when we move this big thing over to the other side. We have and kind of combine things. We get r0 squared over 4 mu times gamma times delta h over delta L. Whoops, that's an L. That is an L. Now, when we plug this all back in to this equation, this needs to go back into here. We can see that we're going to have we're going to have an R0 squared and an R squared, and then pretty much the same stuff multiplied together as a constant out front. So let's just go ahead, let me go back and let's just go ahead and rewrite this now in terms of V after we plug back in. So V now is R0 squared, and I'm kind of skipping a bit of the math here, over 4 mu, and then we have gamma delta H delta L. And that's our velocity, and we note that the maximum velocity, Vmax, is going to occur at r equals 0. Now, if you look in the book, they make a major mistake by saying that this equals that Vmax it occurs at r equals r0, which we absolutely know is not the case. And that's where I think their derivation has gone horribly wrong. We know that the velocity is 0 at the wall, so how can this be? This is a big question mark in my mind, and I think it's just indicative of the fact that they've kind of botched this derivation in the book. So we can plug in r equals 0 for our Vmax. Oh, let me get back to a nice black pen. So our Vmax is going to be, it's pretty easy to plug in right here for r equals 0, and you can just see we're going to get r0 squared over 4 mu times that other quantity. So this is what we get for our Vmax. And note that my value is positive, which is what we ought to expect for a velocity, or a speed in this case. It's not even a vector, so we're pretty convinced that this is looking good. And now when we also rearrange to get our final equation for the velocity, we also have a positive r0 squared over 4 mu delta, or gamma delta H delta L from before, and we can rearrange that to be 1 minus r squared over r0 squared. Okay, so we've got a nice equation here. It's positive. The one in the book is negative. Again, I think that this is indicative of a couple of mistakes that they've made, one being right here, and also their transformation of variables is a bit strange, and I don't, in my opinion, it doesn't work out. So let's now go forward and calculate and just verify this value. Remember, we can do this integral, and we should be getting a positive sign out of this now. So I'm going to go back and let's just calculate Q as being the integral of the velocity over that pipe. And so Q is going to be equal to, again, the integral from 0 to r0, from the middle of the pipe to the edge of the pipe, times the velocity, which is r0 squared minus r squared, over 4 mu, times gamma delta H delta L, and our element of area is going to be 2 pi r dr. And that is because when we are interested in integrating an area from the pipe, our element of area is going to be this little annular ring here, and it is 2 pi r around, and it has a thickness of dr. So the area of that, it has, in one dimension is dr, and then the other dimension is the circumference, 2 pi r. So that's our element of area that we're going to integrate over. And this is actually a pretty complicated integral, and I'm just going to write it all out here as quickly as I can. We pull out a bunch of stuff out front. We've got 2 pi 1 over 4 mu, and the delta, the gamma delta H delta L's all come forward, and then we're left with this. We have an R0 squared, which is going to get integrated from 0 to R of R dr, and we have a second integral of R squared, actually R cubed, because we've got an R squared here and an R. This is going to be R cubed, again from 0 to R0, and that is also dr. And writing this all out again, we have this entire constant, which I'm not going to rewrite, and what we get out of the integral is R0 squared times R squared over 2 evaluated at 0 and R squared, minus R to the 4th over 4 evaluated at 0 and R0. And this thing then reduces to basically R0 fourth over 2 minus R0 4 over 4. And again, we've got the constant out front that I'm not going to write down. And this is like this. So if I can just squeeze this in at the bottom, Q is going to be equal to 2 pi 1 over 4 mu gamma delta H delta L, that's an L, and we have R04 over 4, because that's what this this quantity right here equals. The R0 to the 4th over 2 minus this is going to give you this quantity here. And rearranging a bit gives the equation in the book with a positive sign again. Positive flux, volumetric flux, is going to be over 8, over 8. Man, I'm just not sure I'm going to be able to squeeze that in there. Let me try one more time. That is going to be an 8. An 8 mu, that's an 8, times gamma delta H delta L. Okay, if we go down here and we compare that, we get the same, this is the same equation that I just derived. So we're looking quite good. If we compare this velocity back to the mean velocity that, or the max velocity we have, we can see that, well, let me just go ahead and do that. Let me back up. New sheet. If we actually go back and compare this to the Vmax, we if we determine the average velocity now as this equation, which we've used before, we've got pi R0 to the 4th over 8, now I can draw it, gamma delta H delta L, and if we divide that by the area, which is pi, the total cross-sectional area of the pipe is pi r squared, the pi's cancel, and this cancels 2 of these, and so the velocity, the average velocity we're left with is R0 squared over 8 mu gamma delta H delta L. And if we look back and compare that to the Vmax, we can see that we calculated before, this is just our Vmax divided by 2. So the average velocity is just the maximum velocity divided by 2. And one other thing that we can do is we can substitute in R0 is d over 2, and our average velocity becomes d squared over 32 mu, because this is squared. This gives us a factor of, this becomes r0 squared is d squared over 4, and we're multiplying that 4 by this 8 to get this 32. And that quantity, again, is times the gamma delta H delta L. All right, so we're in good shape. Now, all we need to do is apply the energy equation. Oh, this now is this equation here down at the bottom, and you can see it's positive, like I believe it should be. And so we've derived that equation. Now what we want to do is we want to show that the head loss equals this, and we're going to do that by applying the energy equation. So let's go ahead and do that. We saw before that the energy equation for this simplifies, for a pipe simplifies to this right here. There's no, the velocities cancel out, and there's no pump head. There's no turbine head. And so in a pipe we have this, and we note that we use HF to designate the head loss in a pipe. So this actually equals HL, but we're writing it as HF because it's customary. Now, this is a key. When we plug back into, we're gonna look at our average velocity, and we're gonna expand out that delta H. This was d squared over 32 mu gamma delta L, and we're gonna rewrite H now. But if we look back in our derivation, this should be this value. That's a gamma. The book actually has this flipped. It has a minus sign here. Now you can certainly do that. They've been carrying this minus sign through all the way because they've been defining their piezometric pressure differently. So they have a minus sign out front here, and they have P2 over gamma minus, plus Z2 minus P1 over gamma plus Z1. So this is actually the same equation in the book. And then they rearrange this to bring the constant over to the other side, and we have 32 mu V bar L over gamma D squared is equal to basically the difference in the piezometric pressures. So I'm just going to put this as delta PZ from 1 minus 2. Okay, and so actually maybe I should write that out. I think I'm going to backtrack and I'm going to write that out because it's very key that you understand this step, that this quantity equals P1 delta plus Z1 minus P2 gamma plus Z2. When we compare this to the energy equation up here, this was energy equation, we can see that this quantity right here is equal to HF. All right, so let's, so basically we could move this over to the other side and we would have this same equation with this quantity being equal to HF. So we're going to go ahead and write that out and derive the an equation for this. So this is, again, 32 mu V bar L gamma D squared, and where we have substituted now delta L equals L, the total length of the pipe. So we're now looking at the length of the head loss along the length of the entire length of the pipe. But look at this. This is just a remarkable thing. When we start to rewrite this thing, let's rewrite this thing according to how the pump head should look. V bar squared over 2G. This quantity here is going to be our friction factor, okay? And so we have all these things that we had before. We have the 32 mu. Let me make sure I get this correct. we pulled out the v, so we don't have the v in the numerator anymore. We pulled out the L. So we just have 32, but we also have divided by 2g, so we're going to add a 2g in here, and we are going to write gamma as rho g, and we have pulled out one of the d's. Here's the other one right here, and we have to divide by another velocity because we pulled out velocity squared. So we have this. Okay, so this is going to end up being our friction factor. We see the acceleration of gravities cancel, and we're left on top with 64 mu over, on the denominator, rho d v bar. That's what we have, and this is multiplied by the ratio of the length to the diameter of the pipe and our familiar v squared over 2g. So what we can see now, this is the head loss. We can see that F now, the friction factor, is equal to 64 mu rho d v bar, but rho dv over mu is just the Reynolds number, so this is just 64 over the Reynolds number, using the dimension as the diameter of the pipe as the dimension and the average velocity of the pipe as the velocity. This is the friction factor for laminar flow in a pipe. Laminar pipe flow. So it's a complicated derivation. I believe the book made a couple of mistakes. I believe this is the right way to do it. And we get an equation for the head loss and an equation for the friction factor and positive velocities and a positive volumetric flux, mass flux. So that concludes section 10.5.